right, section 10.2 in trig. We're talking about mean and standard deviation of a binomial distribution. You'll remember back in chapter 7 we talked about how we could find the expected value or the average of a population, the true population average. We called it mu, and it was the sum of a bunch of things, the outcomes times the probability of those outcomes. We actually made a chart, and we put these in list 1 and these in list 2, and then we did sum L1, L2. But we can use a nasty proof from the book, and it can be shown, and that's exactly what you like to see in college. It can be shown, because that usually means that the college professor doesn't want to do it and is not going to require you to do it either. It can be shown that this formula can be proven to be a nice simple one for us. Mu is equal to n being the number of trials, and p being the probability of success. For a binomial distribution. So it's pretty easy to find n and p, multiply them together, and then you have your average. Now, we also would like to know the standard deviation. We know that a stepping stone to getting standard deviation is the variance. And we had a formula for variance, and that was little sigma squared. Call them little sig in the rap world. And that is the sum as I goes from 1 to n of x sub I minus x bar. That's fancy for the deviation from the average. We had to square those because we wanted them to be positive, otherwise they'd add up to 0, and that doesn't really help when you're trying to find an average. So we squared them to make them positive, and then we could add them up and divide by the number of values we have. And that is in itself is called the variance. But we're not really interested in the variance so much as we are the standard deviation. And with advanced mathematics, it can be shown that this is a shortened version of that would be sigma squared is equal to NPQ. NPQ, not that difficult. Q being the probability of failure. Okay, now, obviously we like the standard deviation. Standard deviation, one step away from that is just to take the square root of both sides of that equation. So there's our standard deviation formula, square root NPQ. The few examples that we're going to do from this section are just asking you to find the mean and the standard deviation. So not a lot of tough stuff in this section. For instance, they have a dart throwing question. Example 1, we have the probability 0.8. Yes, I picked a number. Instead, the book doesn't have a number, so I just picked one. So I said, well, there's an 80% chance that we can hit the target. So what would my failure rate be? Well, that would be a 20% chance. So what's the expected number of bullseye throws out of 3? Well, if n is equal to 3 and probability of success is 0.8, then my average would be 2.4. Now, that does not mean you can get 2.4 bullseyes if you're going to throw it only 3 times. That does mean that if I keep throwing rounds of 3 and I add up and average all of those different rounds, I would average 2.4 in the long run. The standard deviation would be 0.693, and we could talk about what that means once we get to the standard normal curve and how that applies to this situation. And that was pretty much example 2, was just calculating that standard deviation. So example 3 is another type of binomial distribution. It says at this particular hospital, 48% of all the children born are girls. That would mean 52% born are boys. In this case, that's what they're calling success, and this is what they're calling failure, not that boys are failures. Okay, I'm sure some of you girls are saying yes, but it's not true. Okay, it's just that that's what they wanted to call their success. All right, so anyway, there's 2,500 trials or 2,500 babies born at this hospital, and of those, 1,200 on the average would be girls, and the standard deviation in this case would be 24.98. And once again, the number 24.98 will be explained later when we get to the standard normal curve. See ya in class.